this industry and all the fascinating challenges that these projects present. Very fast-paced, very unique, highly variable projects. And so I'd like to just kind of present a broad overview of that today and give a little bit of perspective on kind of how these projects take place from start all the way to finish. So as far as the mining process goes, it all starts with the ore. Ore is essentially just rock that contains a valuable mineral like copper, gold, and so forth. So it starts by blasting the ore out of the ground. After the ore is extracted, it can be processed in a few different ways. The first way, which I won't spend a lot of time talking about today, but felt was worth mentioning, is heap leach. And in heap leach, ore is crushed and it's placed in large piles, and it's essentially leached with a chemical solution that extracts the target mineral from the ore. That leachate is then collected, and the mineral is extracted from the leachate solution from there. The other option for processing ore that I will talk about in great detail today is concentration. And that entails transporting the ore to a concentrator plant. The ore is crushed and ground up into soil-sized particles, so nothing larger than sand, and all the way down to silt and clay-sized particles. And then a tremendous volume of water is added to the ore, along with chemicals to extract the mineral from the ore. After the mineral is extracted from the ore, what's left over is a large mass of soil mixed with water as a slurry, and that is the material that we call tailings. And you can think about just the sheer volume of tailings that's produced on a mine. This particular site, this is one of the facilities that I work on mainly. This is a copper mine, and copper is typically found at an ore grade less than 1%. So, for every metric ton of ore that's being produced, less than 10 grams of that turns into copper. And so you've got 99% of that material or more turning into tailings, which is a waste material. And because it's produced as a slurry, it's deposited in an impoundment or a reservoir, and it's retained by a dam. And mines are operational for years, decades a lot of the time, and so tailings are continuously deposited into the impoundment, and the dam has to be raised to keep up with the continuous deposition of those tailings. You can see the tailings sort of create a beach within the impoundment, and then there typically will develop a pond as well. And I'll go into a lot more details about sort of the different components of these tailings storage facilities as well. So kind of already walked through this, but just to give a little more step-by-step process, the material is pulled out of the ground. It's crushed down to, say, gravel-sized particles. It's then ground. This is called a ball mill. So these little steel balls are placed inside this drum. The ore is placed in there, and it's rotated to essentially pulverize the particles down to soil-sized material. It's sent to the concentrator, where it's combined with water and those chemical agents, and our valuable mineral is separated out, and we're left with our large mass of tailings. One option is that the tailings can be thickened, meaning that some of the water is removed from the tailings and reused at the concentrator. This is a way of saving water and reducing water losses within the tailings impoundment. And water is going to be a pretty big topic in today's talk. So that's just the start of it. After thickening, if necessary, the tailings are transported. So this is a video that was taken by a colleague of mine in Peru. You can see that the tailings are, behave like a liquid. It's a material that, it flows easily. Sorry about his finger in there. I'm not sure what he was pointing at, but it is, it's transported as a slurry. And, this is a material that's probably 50% solids content or so. After it's transported, it's then deposited into the impoundment, and it essentially just flows away from the embankment or the dam into the tailings reservoir. As you could imagine, the solid particles will settle out as the tailings stream loses energy, and the water will continue to flow and eventually pond up. Now, I mentioned earlier that these dams continue to be constructed over time as more tailings are deposited within the impoundment. The dams can be raised by a variety of materials, and in some cases, the dam is actually built out of the coarse-grained portion of the tailing stream. In this case, this is one of those cases, and in that case, the tailings are sent to what's called a cyclone station, and it's sent to the cyclones where it's basically spun around or centrifuged, and the smaller particles stay in suspension as the material spins, and the heavier, coarser particles drop out the bottom, and that material becomes your embankment construction material. And it's deposited on the embankment as a slurry, just as it would be in the impoundment. The solid particles are going to settle out, and that water will eventually seep into the embankment. You see this dozer here. Dozers will then push the material out into a constant lift height. The material will be compacted, and the dam will just continue to be raised that way, basically for years on end. Okay, so I've presented a little bit of a intro to the kind of mining and tailings process, and that is sort of becoming clear of what is a tailings storage facility. Well, it is a facility that is meant to store and manage a combination of finely crushed rock and water as a waste product from the mining process. Mines are operational for, at the very least, years, if not decades. This particular facility opened in 2006 and will continue to operate for another about 10 years. And so these are projects that last many decades at a time, and certainly present challenges in continuity of management and continuity of practice. And I'll talk about that a little bit on the next slide. And as I mentioned, water is a huge component of all of this. Water is used at the concentrator, and water is used to help transport the tailings because it's pumped as a slurry. And so managing the water is critical in an environment like here, this particular site in the desert in Peru. Water is scarce, and so it's really important to minimize losses in terms of evaporation, seepage into the dam foundation, and various other components. And so now we've defined what the facility is. What goes wrong? What challenges do these facilities present? I think this first bullet point here kind of says it all. And it's really the big piece of all of it is that safety of people and the environment is of the utmost importance. These are facilities that carry with them a tremendous amount of risk and tremendous consequences if they're not managed safely and responsibly. I wanted to show this video quickly. This is a tailings dam failure from about 3 years ago in Brazil. The dam instantaneously collapses. This is an instance of static liquefaction, and it sends about several million tons of saturated material downslope. And there was a village downstream of this facility, and over 250 people were killed in this event. And so for me, this is really kind of the meaningful portion of what I do for a living, is that this is an industry that has not been managed safely throughout the years. And in our world where metals are only growing in demand, mining isn't going anywhere. And so it's really, really of the utmost importance that we try to make these facilities safer and do everything we can to improve our understanding, improve our management of these facilities. And for me, it's something that's quite meaningful to be a part of that industry that's moving in a direction of improving the safety, improving the environmental sustainability of these facilities in the mining industry as a whole. That second bullet point kind of ties into what I just mentioned as far as the mining industry. The mining industry has not always behaved safely and responsibly. And so it is really of the utmost importance to mining companies to do everything they can to reestablish public trust and ensure that this is an industry that can last for a really long time. And some of these issues that can occur with these facilities, of course, long-term physical stability. As geotechnical engineers, this is really kind of one of our bread and butter items is slope stability. So, you know, are we managing water appropriately? Are we developing saturation within our facility? You know, is there a liquefaction potential? So on and so forth. There's obviously a chemical element as well in mining with all the use of chemicals and to extract the minerals and the natural chemicals that occur within these ore deposits. A lot of that goes into water management, whether it's surface water, groundwater, understanding and characterizing those components of your site. Excuse me. And just two more items that I felt were relevant is that since these are facilities that last for decades at a time, you can often get a situation where a manager or an engineer of record of one of these sites can leave unexpectedly. And with that person leaves a tremendous wealth of knowledge, a lot of protocols, a lot of ideas. And if those aren't passed along correctly, that's when failures like this occur, because items haven't been, you know, carried on through the years that are paramount to the safety of these facilities. And this last piece, this is something that I think pops up in any construction project, in any sort of design, is that you can never be comfortable with deviating from design and an elevated level of risk. These are facilities where anytime that you see something that doesn't quite look right, it needs to be raised, because then if it happens, people start to get used to it, and it sort of snowballs into just being used to deviance from normal operating conditions. So sort of established all the things that can go wrong with these facilities. Well, so what do we do to make sure that we're creating a safe, sustainable, responsible design? It starts with site characterization. It starts with your climate. Is it a wet climate where we have too much water and we're going to have to figure out where to store water, where to discharge water, etc.? Is it a dry climate like I discussed with our sites in Peru, where we're going to have a deficit of water and we're going to need to draw from local water sources and really minimize our losses? Is it a cold climate where we have to worry about freeze-thaw effects? These are all things that you're going to have to take into account in these dam designs. Understanding the local geology, local groundwater, local seismicity are all huge components of these designs. The consequence classification. This is essentially, you know, what are the downstream impacts? Are there going to be fatalities if this facility collapses? Are we going to take out roads, power plants, water treatment plants? Obviously, there's an environmental component with any failure where you have an unplanned release of tailings. So these are all things that you're going to want to understand as you create your project and develop the level of redundancy and sort of a factor of safety on a project. And any design starts with what's called a design criteria and a design basis. So the design criteria is essentially the set of conditions that you have to meet to be successful in your project. And that could be regulatory or just internally defined by the client or the mining company. These are things like design flood, design earthquake, and so forth. Design basis are more on the side of the objectives and what you aim to achieve with this facility. For example, what total mass of tailings do we want to store? How quickly are we going to produce these tailings? How much water do we have available? The second to last bullet point is a really, really big one. And I say here, expect the unexpected. That's not entirely true, because it's silly to think that you'd be able to identify what issues are actually going to occur. But the idea is to make your design flexible so that it can handle potential changes down the road, whatever's going to come up. And that could be ore or tailings material property changes. So maybe there's an increase in plasticity, and now the tailings retain more water than they typically would before. And so now you have a shortage of water. Is your design resilient to be able to handle things like that? Can you handle a change in production rate and an increase in construction schedule? Are you ready for severe weather and climate change? Can we handle a change in ore reserves? Say the mine company approaches you and says, we have 100 million more tons of tailings we need to store. Can this facility manage it? Or could we think about raising the facility and raising the dam? And so these are all things that you have to keep in mind as you work through the early stages of these projects, is making sure that the projects are flexible enough to handle all the curveballs that are certain to come your way. And this last element is huge, and this is something that hasn't always been the case in this industry, is planning for the full life cycle from the very beginning of the project. That means that mining companies have to be able to prove that they're capable of closing a facility before they open it. This is something that is kind of rearing its ugly head now, as many mining companies in the 1800s, 1900s, they mined what they needed to mine, and then they walked away and left it. And that's why we have Superfund sites and reclamation sites all across the U.S. and across the world that are, polluting and causing slope stability and other safety concerns, with no one held accountable. And so we're kind of trying to catch up to close these and make them safer. And obviously, the industry is moving in a direction of including that in the design from the very beginning. And so, speaking of the very beginning, how is it that these projects go from an idea that a mining company has to actually being constructed in the real world? And the answer is that this process can take 10 years, maybe 15 years, maybe more, to get from the conception of the idea all the way down to it actually being executed. And that's because you really want to make sure you're leaving no stone unturned, so to speak, and you're really evaluating every possible avenue, and you're getting input from experts. You're going through several design phases and reviews. You would start with a conceptual design phase where you might take 12, 15 different alternatives, and these are different sites you might look at and develop kind of a basic level design for each of the sites. And that the idea in this phase is to simply weed out what you know is not going to work, and maybe narrow it down to 3 to 5 options. You would carry those forward into the pre-feasibility phase, where you would then start to advance your knowledge base and advance the design and cost estimates, and begin to bring in some more advanced estimates, or assumptions and estimates, I suppose. And you might perform what's called a trade-off study in this phase, and compare those kind of few finalist sites from the conceptual phase. The goal of the pre-feasibility phase would be to ultimately select your final design, or the final design option, and carry that forward into what's called the feasibility stage. Again, with this phase, you would just advance the design, begin doing your analyses, all of your calculations, advancing the design, advancing the field investigations. And this is the phase that's actually suitable for environmental permitting. So there's going to be some very large assumptions and decisions that are going to be made as part of the feasibility stage. Water use requirements, footprints, ultimate elevations, things of that nature, that from that point forward, you're going to be kind of locked in to what the permit says. You move on then to the basic engineering, again, just advancing the design, and then finally detailed design. And this tells the mining company, tells the contractor, the construction company, here's how this thing's actually going to be built. From that design, or that sort of nebulous idea back in the conceptual design phase, now we've taken it all the way through, and it's time to actually build it. We're going to prepare the foundation, we're going to grout, we're going to compact material, we're going to start depositing tailings, and this is how it's all going to come together. There are a few kind of key elements that go into the design of these facilities, sort of key decisions that have to be made along the way. And one of them has to do with which tailings disposal technology is selected. As I said, the tailings are produced as a slurry. And so conventional tailings and projects that I've worked on might be 25% solids content by mass. So essentially it's just a liquid with some suspended solids in it. And you can essentially remove as much water as you want with an increasing level of cost. And that decision is really going to come down to how far you have to transport the material, what type of material it is, how the soil material behaves, what your production rate is, and cost is a huge one. So you might thicken the tailings, which means removing some of the water down to, say, 50% solids content. Paste, you might be more in the 70% solids content range. And then cake, where the material's actually, all of the water's kind of squeezed out, and you end up with really a soil behaving material at optimum water content. The paste and cake technologies are sort of increasingly expensive from the more conventional and tailings type deposition methods. And so I've personally never worked on a project with those. Those tend to be used in smaller scale projects. At this stage of the technology, those options really aren't implemented at large scales, but the industry is moving more and more in these different directions as more technologies are developed. And just to kind of give a little reference, when you're in this conventional sort of thickened tailings range, this material is going to be in, sort of ketchup or yogurt type consistency. And then of course, increasing in shear strength and solids content as you move to the right along that spectrum. I mentioned earlier the impoundment, the tailings facility has to be retained by a dam, assuming you're depositing the tailings as a slurry. And there are several options on how you actually can raise these dams. They all start with what's called a starter dam. And that is essentially sort of a traditional water retention type structure. It might be a zoned earth fill or rock fill dam with a low permeability central clay core. And then over the years, you're going to raise the facility, and you have a few options on how you might raise the facility. The first option is the downstream raise that you see there the upstream raise that you see there at the top. And that involves actually placing your dam raise on top of tailings that have already been deposited. Now, this is a very cheap method because you see you really don't have much fill material to use for each dam raise. It's also a method that carries with it a tremendous amount of risk because you're placing each dam raise on top of tailings material that may be saturated. It hasn't been compacted. And so it presents challenges that the other methods don't. And the industry is really sort of moving away from this technology for that reason. This method has been associated with some of the failures that have occurred in recent years. And that's not to say that this type of facility can't be managed safely. But with sort of the increased scrutiny on mining and tailings in the world, most mining companies are sort of opting to spend a little more money and use a method that's known to be generally a little safer. Sort of the polar opposite of the upstream is the downstream, and that involves moving up and away from the tailings pond with each raise. And the difference with this one is that it is extraordinarily more expensive because you can imagine the volume of material increases sort of exponentially with each dam raise. And you can kind of meet in the middle and do a centerline raise, which at the facilities in Peru that I work a lot on, this is one of them, are both centerline raise facilities. And the dams can be raised using earth fill, some sort of soil fill material, rock fill, or like I mentioned, the cyclone sand tailings material. And so here are just a couple examples of those types of dams. You can see here a centerline raise with zoned rock fill. It remains a zoned dam, so you see this core traveling through the middle of the dam, and then rock fill on the downstream and upstream shells of the facility. Whereas the cyclone sand dam is essentially a homogeneous embankment above the starter dam constructed entirely out of this cyclone sand tailing material. And I can't say enough about water. It's one of the biggest challenges that we face. Water can cause a lot of geotechnical issues with liquefaction and other things, but water is also a very important part of the whole process. And so there's a lot of elements that go into managing water on these facilities. And I'll just kind of touch on a few here. The first is foundation treatment. So before the thing gets built, you want to make sure you have a good contact between your dam and your foundation. You want to make sure you're mitigating any sort of seepage. Part of that is characterizing the foundation beneath the dam. Part of that is characterizing your local groundwater conditions. And you might grout beneath the dam to provide a seepage barrier beneath the dam. You might excavate a cutoff trench beneath the dam to get down to some more competent bedrock material. But it's really important to avoid sort of preferential seepage paths through the foundation and beneath the dam. Another big element is the use of granular filters. Without filters, you run the risk of particle migration, whether it's your underflow sand or the core of your starter dam or any other material really. And filters just help to retain those materials and prevent a piping failure. Geosynthetics can also be used. Embankment under drains and seepage mitigation and collection is a big part of it. You want to be able to collect all of the seepage that goes through the dam and be able to reuse that water. So this is an example of a seepage collection system where the dam would be up valley here. The seepage comes from the impoundment, runs through the embankment, and is collected here, and ultimately it's pumped back to the concentrator plant for reuse. Just a couple more items here. I wanted to touch on instrumentation is a big part of it. Installing piezometers within your dam and within your foundation to monitor your pore pressure conditions and make sure you're not getting elevated pore water pressures. You're not getting rises in your phreatic surface that could potentially cause dam safety issues down the road. And there's a lot of analyses and design, as I mentioned earlier at the very beginning with my sort of day-to-day responsibilities. There's a lot of analysis and design that goes into these facilities. The first is material characterization. It's important to understand what the properties of your tailings material are. What are the particle size gradations? Are we going to have enough coarse fraction to raise the dam out of cyclone sand? Or are we going to have to use a borrow source to raise the dam? Characterizing your foundation, and that's site investigations, that's permeability tests, strength tests on all of the materials to feed into the remaining analyses and understand what the characteristics of the material are that you're working with. One of the key elements of tailings storage facility design is a material balance, and that's where you essentially take into account the geometry of the valley that you're depositing the tailings in, and you understand how you start to predict how quickly the facility is going to be raised. And from there, you can sort of plan your construction schedule and the raises of the dam. This is an example. So this blue line and the green line is your impoundment elevation with time. And then this red dotted line would indicate, okay, here's how quickly we need to raise the dam in order to have sufficient flood capacity within the impoundment. Water balance is also extremely important. Predicting different flows on site and understanding what your losses are going to be in the way of evaporation, seepage into the foundation of the impoundment, different losses at the concentrator, and making sure that you don't end up with a water shortage down the line that you didn't predict before. It's important to characterize the seismic nature of the site, of course, and that's a huge piece of deformation and a lot of these a lot of these stability and deformation calculations that we do. I mentioned seepage, stability, deformation. Those are big calculations that we do just to characterize, the phreatic condition, the slope stability factor of safety, static and seismic deformation of the embankment. We also characterize geochemistry as it relates to groundwater and surface water and reactions that might take place over time, as well as, I just mentioned it, groundwater and surface water being hydrogeology and hydrology, characterizing those aspects of the site and understanding, what our groundwater flows look like, what our surface water flows and during a precipitation event would look like. How are we going to have to collect water, mitigate seepage, and all of these things. So once we create this big, beautiful design in our detailed design phase, it goes to construction. And I would argue that construction is more complicated than all of the design that we do because, it makes a lot more sense when it's on a computer screen. When you get out into the world, things do not look like you thought they would often, and you often run into challenges. That last bullet point should actually probably be first, because there's always going to be design modifications, and things are going to have to get changed. Things are going to have to get updated, and that requires really consistent communication between the designer, like Stantec, and the mining company and the contractor who's actually constructing it. It's important to keep in mind throughout the entire design the constructability of a facility, understanding what sort of equipment is going to be used. Can this equipment work on this slope, or are we going to run into challenges? And probably the biggest part of construction, or of, I guess, confirming that construction is proceeding as planned, is QA/QC. That's quality assurance and quality control. And that is essentially having people dedicated on site to verify that construction is proceeding in accordance with the design. So that looks like observing compaction, testing density after compaction of materials, testing particle size gradations, permeabilities if necessary, inspecting the foundation after it's been prepared. And this would be usually a representative of the engineering company to confirm that, yes, the design is proceeding as we've intended. Well, so after a tailing storage facility is built, unlike most projects, we don't get to just walk away and say we're done, because it has to operate for another, say, 30 years. So as we operate these facilities, there's a lot of challenges, a lot of adaptation that has to occur, and it's really a continuous process to ensure that the goals of the facility are being met. One of those ways of tracking that is called key performance indicators, which would be things like the slope of the dam, freeboard, crest width, all of these different design parameters, and we would measure those on at least a monthly basis, and just make sure that, yes, all of our design parameters are being adhered as we set forth to do. I mentioned instrumentation monitoring, not only phreatic conditions, but also seismic monitoring, deformation monitoring, and so forth. It's important to have an emergency action plan. Of course, you never plan on emergencies occurring, but it's important to plan for them and know what, and have the staff trained on what to do, when something goes wrong, because whether it's big or small, things are always going to go wrong on these facilities, and kind of the monitoring and the reporting of these events is key. I mentioned earlier the term engineer of record, or EOR. Every tailings facility has an EOR, and that's a person who's usually supported by a team who essentially acts on behalf of the design of the facility. So when I talk about myself offering design and operational support, my boss, my direct supervisor, is the engineer of record for these facilities in Peru. And so there's a lot that goes into being an EOR and supporting an EOR. And part of that is the EOR performs usually quarterly, perhaps monthly site inspections. Again, kind of tracking those KPIs and making sure that things are proceeding as intended. It's also a huge piece of that is third-party reviews. We have what's called an external technical review board, where professors and other industry leaders will offer their input on these projects and insight that might get missed when it's all just internal discussions within the company. It's really important to have these external perspectives on the project. And of course, there's regulatory requirements, and there's environmental monitoring that takes place along the way as well. And these are taking place on a monthly basis, often as part of the KPIs. And then, like anything else, periodic adjustments to design might be necessary. You might get 10 years down the road and realize, hey, this thing that we thought was going to work actually isn't. So let's go back to the drawing board and try and figure out a better way to do it. So all these years have gone by. The site is finally all out of copper or gold or whatever it is. Now we close the site. And like I mentioned earlier, this is part of kind of the the whole design process in today's day and age, and it traditionally has not been. In the past, in the late 1800s or early 1900s, the company would take the minerals that they needed to, and they'd leave it looking something like this. And then companies like Stantec and other consulting firms and mining companies have to come in and clean it up. And so we're kind of playing catch up. The industry is as a whole on closing these facilities that were abandoned decades, centuries ago. In today's day and age, that's obviously not part of the plan. Now the plan is to get these facilities closed.